Okay, on to rank. And we do not mean colonel versus lieutenant colonel. So, given n by n matrix A, the set of all the combinations of the row vectors is called the row space, right? Of course, with this familiar denotation, row space of A. So the row space of A is a subspace of Rn, right? So many entries. And row space of A is equal to the column space of A transpose. So if two matrices are row equivalent, then their row spaces are the same. If B is an echelon form, the non-zero rows of B form a basis for the row space of both A and B. Okay, so row reduction doesn't alter the row space. So let's find a basis for row space, column space, and null space of this matrix A. So row reduction makes it equivalent here to B, and so it looks like a basis for the row space, right, as it says, the non-zero rows. So the first, second, and third rows. First, second, and third rows. Actually, that's a basis for the row space of A and B, right? Column space is, of course, right, based on pivot columns. So 1, 2, and 4 are pivot columns. So columns 1, 2, and 4 form the basis. 1, 2, and 4. Okay, got to go back to A for the column space, by the way. Right? You should know why that wouldn't work. If you use B for the column space, we're not going to be able to get entries in this. Right? There's no way to get 1, 7, and 5 with all the zeros here. So you have to go back to A for the column space. So the column space are just the columns of A, columns 1, 2, and 4 of A, right? Because those are the pivot positions. And then finally, yeah, null space we also asked about. So null space you want to use RREF. Okay. It just makes life much, much easier. So we further reduce B to RREF and get C, equivalent to C, which is this. And then we go ahead and solve, right? Because we have a free variable. In fact, we have two free variables, right? We have a free variable. This is not a pivot column, and nor is this one. So x3 and x5 are free. So x1 is minus x3 minus x5, right? These are coming from this right here. x1, x3, x5. And so we can write these parametrically, right? x3 and x5 are free, so they can be expressed in terms of 1, 2, and 4. So we have the minus 1, 2, 1 for x3, 0, 0, right? Minus 1, minus 3, that's coming from minus 1, minus 1, minus 3. There is no x3 there, so it's 0, and then it's 5, and then the 1 for the x5. So this is the basis for the null space. In other words, any vector that gets mapped to the 0 vector is a combination of these two. Okay? So the rank of A is the dimension of the column space. So given an m by n matrix A, the dimension of the column space and the dimension of the row space are the same. This common dimension is what we call the rank. Okay? Also, it's obviously the number of pivot positions, right? So the rank is the number of pivot positions, right? Notice that the rank of A plus the dimension of the null space has to be n. Why? Well, the rank is based on pivot positions. This is based on free variables, meaning non-pivot positions. They're mutually exclusive, so pivot plus non-pivot has to give you the whole thing, right? Pivot plus non-pivot is the number of columns. So we can add a bunch more stuff here to the invertible matrix theorem, right? The columns of A form a basis for Rn. Column space is equal to Rn. The dimension of the column space is n. The rank is n. Null space is 0, and the dimension of the null space is 0, right? No free variables with that invertible matrix theorem. Okay, so we can add those to that list. Again, here's a nice review question. Given the row equivalency of A and B, take a look at it and see what's the rank, what's the dimension, basis for those different things. So that's a nice kind of a combo question there. Okay, and then the homework is oddly similar.